So last time we stopped at this existence and uniqueness of differential equation, and I did pause a little and we said we'll continue this next time because we have that simple. This is partial derivative. So I'm not sure if you take in calculus 3 or you took calculus 3 or haven't taken the class. So I just want to review, spend like a few minutes to review the differential partial derivative before we continue. So last time we have implicit differentiation. This is partial derivative, completely different things. It will come in later section. Okay, so partial derivative. So first we have to have a function of multivariable to have a partial derivative. So we have, let's say, the function of x and y, a function of two variables. And now we function of two variable or more, we can take the partial derivative. We cannot have partial derivative with just one variable. Right, so that first. And now I just want to write the derivative, the definition of derivative, and then we'll see how do we evaluate it. So partial derivative with respect to x. With respect to x. We continue the note later, but for now, just want to review partial derivative. With respect to x, one of the variable. The notation for that is this simple, like del, not del, but partial d. So that is partial derivative with respect to the variable x. We can write like this, or we can just write the subscript. Okay, so that's the notation, and the derivative and the definition is going to be like this. So derivative of f with respect to x. Right, just going to be limit limit this with respect to x. So we take x delta x go to 0, and we'll treat y as constant. To that end, we're going to have f of only the x changes. The y will stay the same. So meaning x variable, y is constant. So we treat y as constant. Similarly, partial derivative with respect to y. We write the partial d over f, partial df over partial dy over f of sub y. It's pretty much the same thing. Partial derivative with respect to y Now we will treat y as a variable. So we'll have delta y go to 0, f of xy minus f of x y plus delta y over delta y. So we treat partial derivative with respect to y, we'll treat x as a constant. In partial derivative with respect to y. Again, we just review partial derivative here, and then we go to the section later. Now let's go to some example. Find the partial derivative. Let's just first thing very easy. Let's say we have the function of 2x squared 2x cubed plus 5y squared. Okay. So if we have a function like that, then derivative with respect to x, we're going to treat this as a constant. Derivative of that is going to be 6x squared, right? And then derivative of that constant. Derivative with respect to x, y is constant. So this is constant. Derivative of constant is going to be 0. So I'm just going to say derivative with respect to x is that. Derivative of this, y is a constant with respect to x. Derivative of constant is 0. So that's just 6x squared. Likewise, derivative with respect to y, x is constant. Derivative of a constant is 0. And derivative of 5y squared with respect to y is 10y. So we give the other variable a constant and just take derivative with respect to it. Okay, it's not the easy one. 2. How about x times e to the y? Okay, I'll just y squared xy squared. Okay, let's say that. Now, in that case, we will treat y as a constant. So in that case, it might help. If it helps, you just write, okay, what is derivative with respect to x now? So from that one, you might rewrite, okay, I haven't taken derivative yet, just going to rewrite. If y is a constant, e to the y is also a constant. So it's just, if with respect to x, y is a constant, y squared is also constant. Right? Also we have k1x plus k2x, and derivative is going to be k1 plus k2. Right? With respect to x, it's just a constant times x. Derivative of a constant times x is that constant. Same thing here. So derivative here we have just e to the y. So derivative of x is 1 times that constant. Derivative of x is 1 times that constant. So that. Now, what is derivative with respect to y? Derivative of y, x is going to be a constant. So derivative of e to the y is still e to the y. And that constant will stay there. Derivative of y squared is 2y. That x is constant. We stay there. And that's we have x e to the y plus 2xy. By the way, if you have any question, please type in the chat, raise your hand, or just speak up. The video is being recorded, by the way. For those who could not be here now. Let's go to something. X times sine of xy. Okay. Now we take derivative with respect to x and then with respect to y. Now with respect to x. With respect to x, you will see that, okay, this is the product. We have something that have x in it times something that have x in it. So this has to be a product rule. So we have pretty much the product rule. So derivative. So u prime v plus u v prime. So x, derivative of that is 1. And then we have sine v sine of xy plus u, which is x, times sine of xy, that is cosine of xy, and then derivative. This is the chain rule, right? So derivative of sine is cosine. So derivative of sine of something is cosine of something. But then we have to have derivative of that something. This is the chain rule. So with derivative of xy with respect to x, treat y is the constant. So derivative of xy with respect to x will be just 1. Derivative of x is 1 times the constant y. So will be y. So this will be sine of xy plus x. Plus x times cosine of xy, and derivative of xy with respect to x. Derivative with respect to x is 1. Y is constant, so be just y. Or so we say sine of xy plus xy cosine of xy. So that is derivative with respect to x. Now with respect to y, now that is different. With respect to y, we still can use the product rule, right? U and v. Not really product rule here, because we only have y in this function. We don't have y in that function. Nevertheless, product rule still work. U prime v plus u v prime. Of course, the prime here is derivative with respect to x. Also in the partial derivative, we can use subscript as well, like that. Okay, so u prime derivative of this I'm sorry, this with respect to y, so this had to be y. Okay, so take derivative with respect to y. Okay, so u prime v plus uv prime, and the prime being derivative with respect to y. Derivative of x is a constant with respect to y. Derivative of constant 0, right? With respect to y, it is 0. And then we have v sine of xy. And then u be x. Derivative of this with respect to y. In general, derivative of sine is cosine. And then derivative of that inside. Instead of the prime there, it is with respect to y. Okay, so that's just the chain rule here. So we have xy, xy. That's 0 times anything is 0. We have x cosine of xy. Now, x times y derivative with respect to y, derivative of y is 1. X is constant, so this is just x. So we have x squared cosine of xy. Right. So that is partial derivative with respect to x, partial derivative with respect to y. And pretty much in this class derivatives, partial derivative, we probably do not get any more complicated than this, even though it could get more complicated, but for this class, probably just that. Alright, I want to also say that if it is the first derivative, we can also have the second derivative. Higher order derivative. We can say derivative with respect to x twice, or we should say f of x. Derivative with respect to y twice, or we can have derivative with respect to both x and then y. So with respect to x first, and then with respect to y, and then we have y first and then x. And later on we can say we see that they are equal. This is called the Clairaut theorem. So mixed partial derivative are equal. But I just want to do one example here. Let f of xy equal to x e to the y plus y to the fifth to x cubed. Okay. Now, I just find f of xx, f of yy, and f of xy. Okay. So f of x, first derivative with respect to x, derivative with respect to x, that derivative with respect to x is 1 times constant. So this is just e to the y with respect to x. With respect to x, this is constant, so that's 0. With respect to x, that is 6 x cubed, 6x squared, sorry. Okay. And now with respect to y, e to the y is still e to the y. X is constant, so we still have x e to the y. With respect to y, that is 5 y to the fourth, and that constant is 0, because that constant with respect to y is going to be 0. Right, so that is derivative with respect to x, derivative with respect to y. Now from here we can say derivative with respect to x and x. So take derivative with respect to x again. That is constant. So 0 derivative of this with respect to x. We have 12x. So that is fxx. Fxy is derivative of this with respect to y. Will be derivative e to the y is still e to the y. That constant with respect to y, derivative is 0. Now this is fy, so let's do fyx. So I just take derivative of this with respect to x. Derivative with respect to x is 1 times constant. And derivative of this with respect to x could be 0 because that is constant. And then f of y. Derivative with respect to y already. So now this derivative with respect to y is e to the y still. And then that constant. And derivative of this with respect to y is 20y cubed. So that is second order partial derivative. Okay. So again, that's just the basic partial derivative. We will not need higher than this for this class. Okay. So that's it. Okay. So we continue from last time. Existence and uniqueness of solution. So if we have the initial value from a differential equation and the condition, and if f and partial derivative of f with respect to y are continuous in some rectangle containing the point, then the solution is it has a unique solution. So solution exists and is unique on that interval. All right, so that's the theorem. How does that work? So if we have condition of y, if this is the solution, and if we have y of x naught equal to y naught, so this is the initial condition, this point. And if we have a rectangle around it where the function and the partial derivative of the function with respect to y are continuous, then we have a unique solution, meaning solution exists and is unique. Okay, so first when we look at this, we have to change to the form of derivative equal to something. It's very important that in differential equation is it have a lot of formulas and a lot of things have to be in the right form to use the formula. And in this case we have partial derivative equal to a function. So we have derivative times 3. So first thing we do is divide by 3. So get to the standard form of y prime equal to x squared minus xy cubed over 3. Okay, so be just that. Or you can write as 1 over 3 x squared minus 1 over 3 xy cubed. Okay, and we have the condition of f of 1 is equal to 6, or y1 is equal to 6. So when x is 1, y equal to 6. Now, when we write in this standard form, the standard form is y prime equal to f of xy. And this is f of xy. Okay, so the theorem says if the function and the partial derivative with respect to y, so we find This is the functional, right? And then derivative of f with respect to y. So with respect to y, that is a constant. Y cubed is going to be 3y squared, and the rest are constant. Yeah, derivative of y cubed is 3y squared, and that is constant with respect to y. Derivative of this derivative constant is 0. So we simplify this, we have negative x y squared. Now, add these two functions are continuous when x equal to 1 and y equal to 6. And the answer to that is yes. Not only that, we can substitute any number in for x, we can substitute any number in for y. So there is no restriction on x and y. In particular, when x equal to 1, y equal to 6, the function continuous. So both of these functions continuous because they are defined for x equal to 1, x equal to y equal to 6. Not only equal to 1 and 6, we have the point x equal to 1, y equal to 6, and there's a rectangle around it. Actually, not just a rectangle around it, it is the whole plane. Like we said, we can substitute any number in for x, substitute any number in for y, so it is defined everywhere. So that particular, it is continuous for a rectangle around it. So we say since f of x, y, and partial derivative of f with respect to y are continuous, on a rectangle containing the point 1 and 6. So the solution exists and solution is unique. So we say there's a unique solution. Okay, so with that, we finish section 1.2. Now we go to 1.3. Okay, 1.3. Directional field. This is a short session followed by another short session. Okay, direction fields. So one technique that is useful to visualize the solution is called the direction field technique. So bottom line is what we have on the standard form earlier, we have was what? Y prime equal to a function. And what is y prime? Well, derivative. And in kind 1, what is derivative of a function? Well, that's the slope of the tangent line. Therefore, we have the direction field. Some say this is a slope field to the field of the slopes. Okay, so let's look at the equation y prime equal to x squared. Now, y prime once again is the slope. Yeah. So the direction field is where we can write a slope. So the slope equal to x squared. We say, okay, what does that help? Well, y prime equal to x squared. So let's say if I have the point 0, 0 here, meaning x equal to 0, right? So let's do this. For the point x, the point y, the slope y prime is equal to x squared. Now, if we have x equal to 0, y equal to 0, actually more important, x equal to 0. If x equal to 0, y prime is equal to x squared, so y prime is equal to 0 squared, will be just 0. So at the point 0, 0, the slope equal to 0. The slope equal to 0, so that is the horizontal line. Now, if x equal to 0, y equal to 5, again, the slope is still x squared, 0 squared, still 0. So that's why point the 0, 5, let's see, 1, 2, 3, 4, 5. So that's still a flat line. So for a bunch of points, if x equal to 1, y equal to 0, the slope is 1 square, x square, 1 square is 1. So at the point 1 and 0, the slope is like that. And we can pretty much just draw all the points like 2 and 2 here. 2 and 2, the slope is x squared will be 4. So a little bit steeper. Yeah, so I use the computer software to draw this. So this is the slope at every point whose whole numbers. Of course, you won't be able to do this on the test, and there are too many drawing at too many points. But regardless, we have the field, and with that we kind of have the flow of the solution. And if we have the initial condition of y1 equal to 2/3, so we have the line of flow that go to 1/3, and with that we have the visual line of the problem. Kind of, we have to draw a bunch of that to have the graph. Right. An isocline for differential equation is a set of all the points in the xy plane will have the same slope. So you see all of this point here, all of this point where x equal to 0, y are different, but x are the same. So the slope are the same in this point. So all the point here we have the same line, we have the same slope, and all the point here we have the same slope. So those called the isocline, the set of all the points that have the same slope. And so usually it's been useful if we graph that. Okay, so we have a bunch of slope, a bunch of points that give us the visual of the solution. Okay. Now, use the isocline method to sketch direction field of that. Okay, so how did that help? Okay, so isocline, meaning that all of the slope equal to constant. So let's say we have the slope equal to x plus y, and we want isocline, so we want the slope, we want this to be constant. So isocline. We have the function x plus y equal to constant. Alright, and the function is x plus y is equal to constant. So pretty much we graph. So first, let's say we have x plus y equal to 0. So in that case, what do we have? Y equal to negative x. negative 1x. So pretty much this line y equal to negative x. I'm going to draw this in pencil. Just a little sketch. Y equal to negative x. So that is the iso line. And everything on this line, we have the slope equal to 0. So slope equal to 0, which is the horizontal line. Okay, that's the first iso line. Next, what if x plus y equal to 1? And subtract 1 on both sides, we have y equal to negative x plus 1. So pretty much just that, plus 1. So we go up 1 unit, and that will be this iso line. And every point on this line will have the same slope of 1, which is 45 degrees. So we have that. And then we have x plus y equal to 2, which negative x plus 2. So negative x plus 2 is going to be this. And now the slope is equal to 2. So a little bit steeper. Everything on that, we have the same slope of 2. So a little bit steeper than 1. And first we can do negative. And that gives us y equal to negative x, negative 1. Okay, y equal to negative x minus 1. And all of this will have the slope of negative 1. 1 equal that way, negative 1 this way. So on the point there have the slope of negative 1. So that is the iso line. I will just keep doing this. Make the function be a constant and draw that line, and every point on that line will have the same slope. We'll just keep doing that and we have the field. And that, of course, at this level, it will be very difficult to get the solution from that field. Okay. Next, if we have a function that only depends on y, derivative, the slope only depends on y, we call that autonomous solution. I just want to give one example here. If the function on the right is p times 2 minus p, okay, and now we're going to plot y with the y-axis. Now p times 2 minus p. Actually, we might, let me turn on the calculator. Okay, and I'm going to graph. By the way, make sure you the video and the audio are okay. If there's anything wrong with the video, please let me know. Okay, so I'm going to graph x times 2 minus x. X times x. Okay, I need to change a little bit. Okay, so it is a parabola that open down, and we can, in particular, it go like this: 0 and 2. So it is above the x-axis, positive between 0 and 2, and negative on the outside. So it's negative, positive, and negative, right? So with respect to y, if it is bigger than 2, the slope is negative. If it is below 0, it's also negative. Between 0 and 2, the slope is positive. So we based on the graph, above the x-axis positive, below the x-axis negative. So that's what we have. Now based on that, based on that, it will be negative here, positive here, and negative there. So we can draw the slope like this. And with that, it look like all the solution will convert to this line. So that is stable. That's what makes it stable. But on this line, it will diverge from it. It will be unstable. So for the autonomous equation, we can write as a function of y. And with that, we find the sign of it. And we can determine if the solution is stable or the solution is unstable. If both of them convert to it, that's stable. It diverges away from it, unstable. So we don't have much in this short section 1.3. We'll go to 1.4. Okay, so this is an application using the calculator or some type of programming. So I highly recommend that you get the calculator to follow this. And this is also a very good lecture. Very good lecture that I put on online for the video. This video is being recorded. So in the future, if you want to go back and see how do we do on certain things on the calculator, you can go back and watch the video. Right. So this is called approximation method or the Euler method, pretty much. Okay. So approximation. So bottom line is what we have is the standard form of the equation. We have derivative is equal to a function at the initial condition of y of x naught. So we will start at the initial condition of this. Okay, then we say, okay, if that is the case, the function will give us the derivative. Derivative is the slope. So we have 1 point x naught. If we want to go to x1, then what is going to be y? Okay, we say if we have x naught to x1, we can base on the slope to go to the next solution. So the approximate solution is going to be there. And then if we want to go to the next step, we trace along the slope, derivative, the slope, go to the next point and go to the next one. Essentially, we get the approximate of the solution. The approximate solution will not be as good as the actual solution. The further away from the initial condition, the worse it gets. But nevertheless, we have an approximation based on the slope and the initial point. Okay, so the Euler method. For the initial problem of derivative equal to a function and the initial condition, let h be a fixed number called the step size and consider the equally spaced point xn equal to x naught equal to nh. So h is the distance between the consecutive point on x-axis. We call that the step size. The smaller the step size, the better approximation. But then again, it will take a lot of, if we want to go from this to this, if we take 3 steps, that's what we get. We might want to go a smaller step size, but smaller step size will take longer time to get there. Might take 6 steps to get there, or 100 steps to get there. But Euler method doesn't matter. Based on the step size, we will go to the next point based on the slope. And so we have the next point, and the solution will be approximately equal to the y, and the y will be equal to the initial y plus h times slope to the next point. So this is the Euler method. Okay, let me just want to write this. Let's say we have the slope. This is very fundamental of algebra. The slope is, say, m is equal to y2 minus y1 over x2 minus x1. Okay, so with that, cross multiply, and you have y2 minus y1 equal m times x2 minus x1. But x2 minus x1 will be just an h. And m being the slope is the same thing as the derivative. And we have y2 minus y1 equal to derivative times h, right? If you want to solve for y2, we will plus y1 on the other side, plus this is the derivative. Derivative is being the function times h, and plus that is the Euler method. Right. So let me pause the video here a bit. Alright, so as mentioned, this section there will be one question on the test where you actually need to use the calculator for programming. Okay. Of course, the step will be in the next part, the next page. Alright. So let's move things around a little bit. Just a second. Okay, we need the calculator there. So okay. Right, good. Now, so let's look at the problem. Solve the initial value problem. Y prime equal to x times square root of y. Y of 1 is equal to 4. And if we use the step size of h equal to 0.1, so its step is 0.1. Okay. So I just want to move my video a bit. Okay. Need that space. Okay. So now the step size is 0.1, and we have here meaning that x is equal to 1, y is equal to 4. In particular, we call this as x0 or x0, y0. So that's where we start. Initial condition, that's where we start. And that's what we have here. 1 for x and 4 for y. Okay. That's for the first step. Now, the x will be very easy. The step size is 0.1. So we just increase 0.1 every time. So that's 1.1, 1.2, 1.3, 1.4, and so on. So that's easy there. Because the step size 0.1, we increase 0.1 every time for x. Now, the y is the one that we need to be updated. Now, if x, first we will find the slope. The slope is x times square root of y. Now, if x is 1, square root of y is 4, so 1 times square of 4 is going to be 2. So the slope is equal to 2. So the y, when we have y is n plus 1, the next y is equal to the previous y plus the slope times h. So we find the slope times h. The slope is in this case 2. And so we start with this 4. The previous y is 4 times 2 times 0.1, the step size of 0.1. And we have that. And with that, we can calculate the next slope. The slope being x times square root of y. So in this particular case, x times square root of y. Okay, so put a calculator. (1.1) times square root of 4.2. Oh, and we have 2.254 something. Okay, let's just give the 2 decimal places. 2.254. Okay, 3 decimal places. So that update the y. Get the slope. Now the next y will be updated based on the previous y. So we go 4.2. By the way, if you do this on the test by hand, that's perfectly fine. Going to plus the step sign of 0.1, that's constant. Always 0.1 is the step times the whatever the slope we get. And we get 4.2 plus 0.1 times 2.254, and that gives us, sorry, here 4.4254, and then we update. It will be 1.2 x times square root of y, which is this guy, and we just keep doing that. As you might imagine, this is a nice problem when we can just use Excel. That will work just fine. We just do just that, but for now 1.2 times square root of 4 times 4.254. Okay, and that is 2.5244. Okay, and we keep doing that. Now we're just updating this. With the step size of constant of 0.1 times that. Okay, so that's good, right? And we just keep update, get this, and then get that, and then this, and just zigzag like that. So let's see some Excel here. Okay. Don't worry, I want to capture the screen. I just want to open Excel first. And now I will do the capture. Okay. Test phone. I should just have the Excel on your screen now, right? Okay. Video and audio should be fine, right? Yeah, look like it. Okay, so now I will have n will be 0, 1, 2, and so on. So I cannot do that. It is okay. This pattern. Okay, so we have that for n. Now x will be just we start from 1 and 1.1 and 1.2. Let's say if it get the idea. Okay, so it's good. So we have x on the axis there. Now the y. Initially it is going to be 4. Okay, the next step is a little more difficult. This is going to be slope. And the slope is equal to this cell, x, times square root, okay, XQRT, square root of that. Okay, so we have that too. And this cell, focus on this. Oh, sorry, I want that. Okay, now this is equal to the previous one plus the step of 0.1 times whatever the slope we have previously. That 4.2. Okay. And then with that, we can copy the formula. And that 2.25 something. And then with that, we can have the rest. So this is the function where we have x values, and this is y values. And this is the solution. Okay, just let me do this real quick. Yeah, that. So we have the solution here. If you want to graph that, hopefully, we do the plot, insert, recommend what to do. Okay, this. Yes, so that is the plot of the function. And x values horizontally and y values vertically. So this is the solution as a graph. It's very nice. So very simple. We just do this and copy and paste and generate the rest of the formula. Right? So that's nice and all with Excel. Very simple. Because this is the recorded video. So if you need to, you can always come back and watch it later. I'm going to post that later. Okay. The problem is you cannot use the computer, maybe Excel on the test. So in that case, you have to be able to do this by hand or the calculator somehow. So this is it. So on the next page, this actually will be what we need. So in this problem, we start with h is equal to 0.1, that's the step size. And we have x and y equal to 1 and 4. And we update the x with this, we update the y with this. Okay, so that kind of like the pseudocode. How do we enter that on the calculator? So instead of write h equal to 0.1, we have to store, say, 0.1 store into h. By the way, for this calculator, I have to do this real quick. Just make sure that it is in a classic mode. The classic mode. So that means that whenever we type the line, we just keep going on. It will not show the dot dot dot. So at least you see everything you type. Okay, so in this case, we have 0.1. The store button is this button, store into h, alpha that hat. So that means h equal to 0.1. That is the initial step. Okay, that's good. Now a little more confusing here is we have x naught, y naught, and then x1, y1, x2, y2. So there are too many. We cannot just have x and y in here. So instead of that, we use the list. And x is, we use the list, which is, if one list will be second and one, that gives you the list. On this list, the first value is going to be x, the second value will be y. So in that case, we say L1 of 1, the first component is equal to x, and L1 y equal to L1 of 2. So the list will be initially second curly bracket 1 comma 4 closes. So we have that list, we have two components. The first one is x, the second one is y in the curly bracket, and we store that into A1, 1 and 4. So the list will have 1 and 4. And now we have to update the list. To update the list, you see L, I'm just going to type and explain as we go. So the list will be updated like this. We start with A1, 1, which means x, plus h. And so this is update. So this is the new x, the old x plus h. And now we have the old y. This is y, the old y plus h times the function. The function will be x times square root of y, right? Where x is A1, 1. And then times square root of A1, 2. Okay. And now so you can close the curly bracket. With that, you see, before the parentheses here, before the comma, you update the x, or x plus h, or y plus h times x times square root of y, and we update that into this one. So that's pretty much it. And now we have 1.1 and 4.2, and hit enter again. 1.2 and 4.4 something, and just keep hit and enter, and you have the new values for x and y, new x and y, new x and y. So you have the values. So this is just like what we have with Excel. Again, we cannot use the calculator, cannot use the computer on the test, so you have to be able to use the calculator. If not, you can always make a table like this and do it by hand. Okay, now with that, let's practice on this one. Use Euler method to approximate this. So we have this is the function y, and this is the initial condition. So from that, we will say pseudocode x naught is equal to 0 and y naught is equal to 1. And from 0 to 1, okay, and using 5 steps, find the absolute error compared to, okay, worry about that later. 5 steps, and each step size is 0.2, so h is equal to 0.2 initial condition, like that. After that, of course, the x will be updated as the old x plus h, so plus the new step size. And the new y will be updated with the old y, so the next n plus 1, the old y sub n, plus h times the function of xn, yn. But the function is just what? Just y. So this is just y sub n. Yeah. So we have yn plus 1 equal to y sub n plus h times y sub n. Yes, so that. Now put on the calculator. We start with 0.2. This is what we type on the calculator. 0.2 store into h. And then the updating step, I'm sorry, the initial step, 0 and 1 store into L1. And then we update the x and y in one step. This is the old x plus h. Now this becomes the new x. The old y plus h times y, the old y. So times L1 2, pretty much that, and store to L1. Okay, now let's try this. 0.2 store into h. Initial values of x equal to 0, y equal to 1. And now the updating step. We start with an old x plus h. So the old x plus h, that gives us the new x. The new y is equal to the old y. L1 2 is y plus h times just the old y. Sorry. Okay. The old y plus h times the old y. Right. and then we just need to close it. Second parentheses, store back into L1 to update it. So we have 0 and 1. Oh, wait. Sorry. Yeah. Okay. So the solution will be as the table like this with x and y. X is 0, y equal to 1, that initial. Next we have 0 0.2, 1.2. We know this 0 0.4, 0 0.6, 0 0.8. And then the next one is 1. Sorry. Okay. 1.44. 1.76, 728, 0.8, 2.0736. One more time, 1 and 2.48832. And the question, I will not ask you to compare that. Just find the solution at x equal to 1. So we say when x equal to 1, y equal approximately equal to 2.48832. Okay, so that's how we solve the problem using the Euler method. Right. Next, let's use Euler method again for this problem. Initial condition, that the function, the step size 0.25. Right, so again, at home you can use Excel hand or by calculator, whatever method, but on the test you can only have the calculator, and so it might come in handy to do all this. So first we have h is 0.25, that is the step. Now we said initially we have x naught is 0, y naught is 2, and then update the x. By just plus h, and update the y by the oy times the function being just y times e to the x, so yn e to the xn. So that is the pseudo code. Now translate that into a little program on the calculator. I will write this h equal to 0.25, 0.25 store into h. Initial 0, 2 store into L1. Update L1 1, which is x plus h. So old x plus h, that new x. Okay, new y is equal to the old y plus h times old y times a to the old x. Old x is L1 1. Okay, close that and store into L1. Okay. 0.25 store into h, right? Initial second parentheses have to be second parentheses to get the curly bracket. 0, 2 second parentheses. Store this into L1. Okay, 0 and 2. Now the updating step. L1 of 1 plus h. So that updating the x plus h give us new x. And then y plus h times the function give us new y. So the old y plus h times the function is y e to the x, or y times e to the x. Okay, e to the x is L1 1. Okay, I will close that and update store to L1. Okay, update x, update y with that function h times y times e to the x. Okay, I think we draw the horizontal table, that would be better. X, y. Initially x equal to 0, y equal to 2. Now we increase the step every time. 0.25. Okay, so now we just copy the values 2.5. Okay, 3.3, 4.66, 7.13, 11.978, 22.43, 47.56, and 115.99. So that's the idea. Yeah, we just keep doing that. So again, on the first test, actually on the midterm, you will have a problem like this where you have to write little program and do the on the calculator. It will save you a lot of time. It will just use a calculator doing this. Doing by hand, it will take a while to get there, especially with all the decimal places along the way. Right. So with that, we finish section 1.4, and I think we just stop here. At least we do something today. Just want to this week we do something this week. So I think we continue. We start chapter 2 on Monday. So let me stop the video here.